All right, let's go ahead and get started. So the name of this lecture is Lecture 5. It's Bonding. Lecture 5 is Bonding and nomenclature. Nomenclature is a fancy way to say naming. Nomenclature.
I just call it naming.
And formulas. I don't know why they don't just call it naming.
Why do they have to be fancy?
Because they're scientists. Scientists want to be fancy. All right, so here, so you
I'm
can...
jealous of all the English.
So you can see it from the back. Lecture 5, bonding and nomenclature and formulas. All right, so bonding. There are two types of bonding. There's ionic and covalent. We're going to be talking mostly about ionic today. And ionic bonds happen between a metal and a nonmetal. Metals are on the left-hand side of the periodic table, and nonmetals are on the right-hand side of the periodic table. Gentlemen, you want to get your notes out? Yeah. Covalent bonds happen between nonmetals and nonmetals. You can draw a heart.
I promise you I can.
All right, draw a plus then. Draw a little plus. So covalent bonds we're really quite familiar with because we're alive. We're a living thing. Almost all living things are made up of covalent bonds. Also, plastics are covalent bonds. All of the fuels that we use are covalent bonds. So covalently bonded things pretty common in our life. But today we're going to be talking about ionic bonds. And ionic bonds are kind of common in our life as well. Now, metals and metals. Notice there's not a bond up there where there's metals and metals. When you combine two different metals together, it's actually not a bond, it's a mixture, and we know of them as alloys. So metal alloys are often used, for example, steel is a metal alloy, bronze is a metal alloy, and then, so we have alloys in our tires, you know, the rims of our tires. What we do is we take the best of two worlds, we melt them together, and they become a nice mixture, and you get the properties of maybe two metals or three metals, depending on. My wedding ring is actually a cool piece of art. It's a Japanese art making called Moka Magame, and it is the art of metal folding. So the Japanese swordsmen, or the people, they're blacksmiths basically, would take metals and fold them, and then they make their swords out of them, and the swords were very, very strong because of this action of folding metal with metal. But it's not a bond, so I wanted to point that out. It's a mixture. So, yeah. At some point, if you want to come look at my wedding band, it's kind of cool because it looks like mokame, I guess, is Japanese for tree, like tree bark or tree, you know, the way a tree would look.
Tree rings.
Yeah. And that's kind of what my wedding band looks like. So let's take a little review about our periodic table. So let's sketch our periodic table. So on the left-hand side, we have metals. And then you've got this staircase. Oh, that is not what I needed to do. You've got this staircase here. This area, or this, darn, sorry, my thing keeps switching over to a eraser. This area is called metalloids, the staircase area. And then this area right here is our non-metals. And we don't concern ourselves with the F block down here too much. Those are mostly, well, they're often synthetic, meaning man-made, or there's some, I don't know what those are considered, honestly. So we got metals on the left, non-metals on the right, and then around the little staircase area, we've got metalloids. So we've got our non-metals. And then remember, hydrogen is our non-metal over here. We've got our metals. And then we'll make this section. Here's our metalloids in this region. I want to remind you of one specific trend that is important for ionic bonding, and that is the ionization. So what ion do you turn into? So everything in the first column, this is taking it way back. Remember the electron configuration, everything here, the outermost shell was the S1. So valence electrons are the outermost electrons. They're the electrons involved in bonding, and we're now talking about bonding. So if you have one valence electron, you would rather give it away than gain 7. Remember, you're trying to achieve octet. So everything in this first column tends to be a positive 1. Everything in the second column tends to be a positive 2. Our transition metals, this region right here, they are in fact cations. Remember, cations are positively charged, but there's no real trend. They could be +1, +2, +3, +4. I think there's some that are even +6. So we're not going to concern ourselves too much with those. We'll get to them because they do, I mean, obviously they're involved in bonding, but there's not a real trend other than they're positive. Then this first column here is +3. Then we have this plus or -4 column. Then it starts going into the negative. -3, -2, -1. I didn't draw very good, did I? Oh well, you get the point. And then the last column is neutral. One of my students pointed out in first period, like, here's oxygen. It is 1, 2 away from the noble gas, so it's a -2 charge. Or phosphorus is 1, 2, 3 away from noble gas, so it's a -3 charge. I don't know, that was just a different way to look at it. It's how far away are you from the noble gas. That helps you remember -1, -2, and -3. All right, so let's look at some of the properties, physical properties. Let's first look at what are some physical properties of metals. So what do you guys notice about metals? Yep, they're hard. Yeah, they're often, can I go back, you said, like that? Is that good enough? Okay. Yeah, so they're often solids. They're hard. Maybe they're dense. What else do we know about a metal? Visually, there's one thing that tells you right away it's metal. Yeah, it's shiny. Good. Oh, I missed it. Sorry. Shiny. Do you have it, Isabella? Yeah. They are good conductors of heat and electricity. They are malleable. So malleable is a fancy word for, flexible. You can manipulate it, or you can hammer this thing into a big sheet, right? So malleable, flexible. You can smash into a sheet. Like aluminum foil is a common one, right? It doesn't just crumble all apart, it stays aluminum foil. We can rip aluminum foil, right? You can cut it, but if you don't cut it and it's just there, I mean, it is very, very thin and it doesn't crumble all apart. It sticks together, and that's a property, a physical property of metals. Another physical property is this word ductile. Ductile means that you can pull it into a wire. Obviously, copper is one of the best, the most frequently used wires. It's really good at conducting electricity. It's fairly cheap as well, and there's a lot of it. But this idea that an atom can be in single file line and still stick together is a property of metals. Non-metals, you can't do that. You don't get to pull them into a nice thin wire or smash them into a nice flat sheet or shape them into anything you want them to be. Metals, when ionized, are cations. So metals are positively charged when they're ionized, meaning their electrons are removed.
So the electrons are removed from cats
From cats, yes.
because it says cation.
Cation, yes. That's how I remember, because cats are positive. They're soft and cuddly, sometimes until they scratch you. All right, so let's look at some of the properties of nonmetals. So nonmetals are non-shiny. They're dull, often. They are often gases. And they are brittle. So if you tried to flatten them all out, you couldn't. They would just crumble almost into a powder or a sand. They're both cations and anions. But mostly they're anions. Mostly they are negative. And this has to do with the fact that they are on the right-hand side of the periodic table. They are so close to being a noble gas, they would rather gain electrons from the universe to be negative. Yeah. Is that good? There we go.
Jeez.
And then the last group, metalloids. Metalloids, also sometimes called semi-metals. Semi meaning like sorta. And basically metalloids have both metal and non-metal properties. So, like for example, silicone, and silicone's right here, number 14 on the periodic table, Si, right next to aluminum. It's shiny, but it's brittle. Silicone is shiny, but brittle. It's weird, like you think it's a metal, and then you can just take it and snap it in half, and you're like, yes, I'm super strong. I just broke metal in half. No, it's a metalloid. It's a brittle thing. So you couldn't hammer out silicone and have it be a flat sheet, or you can't pull it into a wire at all. It just crumbles, almost like how dirt does, or if ever you've seen sulfur, it's like a yellow powder, and it just kind of crumbles into a powder after a while. Yeah. So, yeah, I don't know what property glass is exactly. I mean, glass is a combination of stuff, because you can blow glass, right? And so you can shape it and malleable, and you can also pull it into thin wires. So I don't know, but it's also not a pure element. That's a good question. But I don't know what you'd call that. Actually, it probably is nothing because it's a compound. Yeah. And that brings up a good point. When, for example, hydrogen and oxygen, they're gases. But when they come together, most of the time they're in liquid form, right? It's water. So once you have something bonded, they don't necessarily have the same properties as they were before. They take on new properties. And so that's why glass isn't a metal or non-metal, it's its own thing. Yeah. So semi-metals are mostly cations. Or more frequently, involved in covalent bonding. And in covalent bonding, we're going to talk more about that. We'll start to explore it on Friday, but we'll talk more about that later. And covalent bonding is not giving and taking electrons, it's sharing electrons. So we'll get into that in a few days. All right, well, we've got to figure out how to do the chemical formula. How do we do chemical formulas for ionic bonding? Ionic compounds. So when things come together to bond, there's a goal. And the goal is to combine two or more elements so the overall charge equals 0. Combine two or more elements so the overall charge equals 0. And remember, an element, you guys, is from the periodic table. And it is a pure substance. So the best way to learn how to do this is by example. So, let's say we have some sodium, and it's going to bond with some chlorine. So what is the symbol? So get your periodic tables out from the back of your book. In fact, you have homework tonight in your book, so you need to take it home anyway.
I already did it.
All right, so grab your books and look at the periodic table. What is the symbol and what is the charge for sodium? So what's the symbol? Sodium. It's on the left-hand side.
SI and then Cl. SiCl.
Here we are, sodium on the left-hand side. So Na is the symbol. What charge does everything in this column have? Plus 1. So you just do a plus. Okay, chlorine is on the right-hand side of the table. You see it over here? So what's the symbol? It's Cl, and its charge is minus. How many of each do you need to neutralize to make the overall be charged to be 0, charge neutral? You need one of each, right? You've got a plus, you've got a minus, you put them together, and when you put them together, you write it like this. You just smash them all together and you get rid of the charge. So notice there are no charges. Because it's charge neutral or 0. It's charge neutral, or what we call 0, right? Sometimes I'll see students, don't write this down in your notes. I see students do this. They do NaCl and they smash them all together, but they leave the charges there. That's not correct. Once they have bonded, they're no longer charged. So this is not the correct way to write that. You just write it NaCl and the charges go away. So now there's some rules for naming. The cation is the first element. Always. The positive one always is first. And the anion is the second element. And it always goes second. So the cation, you just use the same name from the periodic table. The second element, what you do is you do the root of the name. And then you change the ending to "ide." So how would we name NaCl? Well,
Sodium
Na
chloride.
is just sodium. Oops. There we go. So Na is just sodium. And then we take the root of the second, chlorine. So we take the root, which is chlor, and we change the ending to ide. So this is the root. Sodium chloride. And that's it. That's how you do it. So we're going to do a couple of examples here, and then I'll have you guys do a little practice. What time do we get out of here? 29? 33? Oh, we've got plenty of time. All right, let's do calcium and bromine. Let's do that. All right, what's the symbol? What's the charge? What's the symbol? What's the charge? So find it on the periodic table. And show me on your fingers what the charge is.
Ca plus
Show me
2.
on your fingers what the charge is. Good. I see 2 of you, 3 of you, 4 of you. Come on, give me some peas. Plus 2. Yeah, you get it. That's my way for you guys to throw out the P symbol. Calcium, here it is, right here. So it's Ca. Or Vulcan. Are we doing Vulcan? Yes. And it's got a +2 charge. In chemistry, the number comes first and the charge comes second. You know, the plus or the minus sign, depending. I don't know why that's the case. Math, you do the charge in the front of the number. In chemistry, you do the charge at the end, or the sign at the end. All right, bromine. Br. And what's the charge on bromine? -1. Yep, it is one away from being a noble gas. It's right here, so it's 1 away. How many of each do you need? So here's a way to look at this. So you got calcium here with 2 lonely protons. And then you've got bromine, that's a charge negative. So look, these guys will neutralize, and these will neutralize. So how many bromines do you need for every 1 calcium? 2. The way that you write that is you smash it together, and you put a subscript 2. So if it's a subscript, that means the number's down below. That's telling you how many. And notice the 2 comes after the bromine. There's no subscript by calcium, so how many is there? If there's no number there, then how many is assumed? 1. Right, so you don't have to put the 1. It's just assumed. It's not 0. It doesn't mean there's 0 there. So calcium bromide. Oh, there's the name, calcium, and then bromide. So there's the name. So remember our goal. Our goal is to combine these elements so that they are charged 0. So let me give you another example. This one's a little bit harder. Magnesium and phosphorus. Magnesium and phosphorus. So look at magnesium. Show me on your fingers the charge. 2 of you know this? 3 of you? 4 of you? 5? Ask me a question if you're not sure of the charge. Are you guys finding magnesium on the periodic table? That takes time. It's on the left-hand side. Did you find it? There it is. It's in the second column. So you're right, all of you guys throwing up the peace sign over there. Magnesium is a +2 charge. All right, phosphorus, what's the symbol? P, and it is a -3. Yeah, it is P right here, phosphorus, and it is 1, 2, 3 away from being a noble gas, so it's going to gain 3 electrons. So remember, we have to figure out how many of each we need. Like, the question is, how many magnesiums times this positive charge? How many phosphoruses times this negative charge to equal 0? So how many of each do we need? Huh? Somebody want to take a shot at this? Sabrina?
3 magnesium, 2 phosphorus.
3 magnesiums. If we put a 3 right here, that would give us a overall +6 charge. And if we had 2 phosphoruses, that would have us have an overall -6, so that would equal 0. Yeah. So this is a way to look at it algebraically. So that means our formula is Mg3P2. We need 3 magnesiums for every 2 phosphorus. If you liked it the other way that I did it, magnesium, so magnesium has 2 lonely protons, and you have a phosphorus that's got 1, 2, 3 electrons. So those guys will neutralize and those will neutralize, but the phosphorus has a leftover electron. So you'll need another magnesium, which comes with 2 protons there. So that'll neutralize, but now you've got a leftover proton. So you need another phosphorus with its 3 electrons. So that'll neutralize. Now you have 2 left over. So this is another way mathematically you could do this, if this works for you, until all of the pluses have a minus together. And you notice there's 1, 2, 3 magnesiums and 1, 2 phosphoruses. And that is so they combine, so they're overall charge neutral. So what's the name of this one? Magnesium phosphide. Yeah, magnesium phosphide. This is where you're just going to get used to magnesium. I have students ask, like, why isn't it phosphoride? Why is the root phosp? Why isn't it phosphor? I don't know. I don't know why. So it's phosphide. Like, for example, oxygen. You don't say oxygen. You just say oxide. Or nitrogen. You don't say nitrogide. You say nitride. So you'll get used to it, and if you make a mistake, I'll correct you, and we'll go from there. Yeah, it's just a matter of getting used to the naming. If you're fortunate enough to know 2 languages, your brain is already wired to pick up new languages. This actually might be quite easier for your person who's monolingual like me. So bilingual, trilingual folks, you're at an advantage because your brain is wired. Lucky you, I wish. Huh? quite done. I want to give you some practice, and then I want to walk around and help you. So I'm kind of done lecturing, but let me give you 3 practice problems that I'd like you to work on right now. So what if we had lithium plus oxygen? And I want you to give me the, oops. I want you to give me the formula and the name. And then let's do magnesium and sulfur. And then aluminum and fluorine. So figure out the symbol and the charge. Figure out how many of each you need. That's how you make the formula. And then the rules for naming. Cation is first, anion is second. Change the ending to "ide." Boom, you're done.